Hi, this is Barrett Givens, and in this video, we're going to talk about a lemma with some facts about basic open sets and open sets. Whenever you have a set X with a topology T generated by a basis B. And just as a reminder, in this class, we're using some slightly different definitions than what you might see in a typical topology class. So in this class, a basis is defined as being a collection of sets that satisfies these two properties. One is the coverage property, that every point in your space is in one of the basic open sets. And the second is an intersection property, that whenever you take the intersection of two basic open sets that have non-empty intersection, then around every point in that intersection, there is a third basic open set that is inside of the intersection. And then we've defined topology to be that open sets are defined as unions of basic open sets. Okay, so here are some facts then whenever we have this situation. So we know, for example, that in any topology, the empty set is open because that's part of the definition that we're using for topology. But in fact, the whole space is always an open set. It doesn't matter what our basis is, what our topology is, the whole space always has to be an open set. Secondly, whenever you intersect two basic open sets, their intersection might not be a basic open set, but it will be an open set, okay? Any union of open sets is open. So when you union up a finite union, an infinite union of open sets, any sort of union of open sets is open. And when you intersect two open sets, their intersection is also open. So in this video, I'm going to go ahead and prove all three of these using our definitions of basis and topology. Okay, so proof. Let's do one first. So we want to show that X is an open set. Our definition of open is that it can be written as a union of basic open sets. So for every little a in capital X, there is a basic open set, B sub a, such that little a is in B sub a. That is the first part of the definition of a basis, that we have this coverage. So that means that X can be written as the union for all little a in X of B sub a. So essentially that when we take our space X, every point has a basic open set around it. And so if we just take all of these basic open sets for every possible point and we union up all of the basic open sets, we're going to get all of X, okay? And so therefore, by the definition, X is a union of basic open sets. So X is open. Okay, and again, that doesn't matter which basis it is, any basis, any topology, X is always an open set. All right, secondly, let's let B1 and B2 be basic open sets. Now this one is going to feel just like the one we just did, okay? I want to show that B1 intersect B2 is open, so I want to write B1 intersect B2 as a union of basic opens. Well, for every C in B1 intersect B2, there is a B sub C such that little c is an element of B sub C, which is a subset of B1 intersect B2. So I claim that in this case, B1 intersect B2 is equal to the union over all of the C's of B sub C. So let's draw a little Venn diagram for that as well. B1, B2. And then every point that I take in here in the intersection, there's a basic open set. And those basic open sets can't go outside of the intersection because that's part of the definition, that each one of these basic open sets containing a point is contained in the intersection. So when I draw these open sets, they all have to stay inside the intersection, but every point in here is contained in one of them. And so this is what we've called the union lemma. So by the union lemma, this is true. Okay, my handwriting is terrible here. That is a C, okay? So B1 intersect B2 is written as a union of basic open sets, and thus B1 intersect B2 is open, because the definition of open is that you can be written as a union of basic open sets. Okay. And then the third statement, any union of open sets is open. So that one, I would say, okay, each open set is a union of basic open sets. And now we take a bunch of open sets. So each one is a union of basic open sets. So we take a union of unions. That's just like a super union, okay? Um, a union of unions of basic open sets is open. Okay. I'm just not going to say too much about that one. You're just imagining each one is a union, and then you union all those together, you just have an even bigger union, which is still open. All right. And then finally, let's let U1 and U2 be open sets. The definition of open that we're working with here is that a set is open if and only if it can be written as a union of basic open sets. So U1 looks like a union over some alpha of A sub alpha, where A sub alpha is basic open. So I don't know if it's a finite union, an infinite union, I don't know. U2 is a union over some indices beta of B beta, where each B beta is basic open. So U1 intersect U2 is the union over the alphas of A sub alpha intersected with the union over the betas of B sub beta. So I'm taking a whole big union of basic open sets, another big union of basic open sets, and then I'm intersecting those unions. So I have a union of sets intersected with another union of sets. Luckily, we have some laws regarding unions and intersections of sets that allows me to simplify this. This looks like the intersection. Sorry, I take it back. This looks like a union over all possible alphas and betas of A alpha intersect B beta. Okay, so these are one of the facts about how unions, taking intersections of unions. All right, now each one of these A alpha intersect B beta, those are basic open sets. So this is like a basic open set one intersected with a basic open set. This is an intersection of two basic open sets. What do I know about when I take an intersection of two basic open sets? When I take an intersection of two basic open sets, the outcome is open. So by part two, A alpha intersect B beta is open for each alpha and beta. And so U1 intersect U2 is a union of open sets. It's a union of sets that I know are open by part two. So then by part three, U1 intersect U2 is a union of open sets. By part three, any union of open sets is open. Okay, and so we've done it. So using our definition of basis and topology, we showed that these four facts would have to be true. All right, thank you for listening.